In some of our previous classes, we have already discussed this topic in some of our previous classes, and we have already had a look at this topic in some previous classes, but we'll just revisit this topic again. So the heat capacity at constant volume and heat capacity at constant pressure. So whenever you want to calculate the heat capacity, there are two ways of doing it. One is at moderate temperature and one is at high temperature. So moderate temperature, if it is a monoatomic gas, and suppose you want moderate temperature, Cv is 3R by 2, Cp is 5R by 2. Now, why does this happen? Because in case of a monoatomic gas, there are 3 degrees of translational freedom only. There is no degree of rotational freedom or any other type of degree of freedom is not there. So Cv and Cp are 3R by 2 and 5R by 2, and if the temperature is high, then also Cv is 3R by 2 and Cp is 5R by 2. So if it is moderate temperature, Cv is 3R by 2, Cp is 5R by 2. If it is high temperature, Cv is 3R by 2, Cp is 5R by 2. Now let us go to diatomic. Now in case of diatomic, what happens? At moderate temperature, there are 3 degrees of translational freedom and 2 degrees of rotational freedom. So 5R by 2 and 7R by 2. But at high temperature, there is 1 degree of vibrational freedom. Now the calculation goes like this, that if it is translational or rotational, then for each degree of freedom you have to add R by 2. Like for example, Cv for diatomic, there are 3 degrees of translational freedom, so 3 times R by 2. There are 2 degrees of rotational freedom, so 2 times R by 2, and 3 times R by 2 plus 2 times R by 2 is 5 times R by 2. And Cp, though you know, is just Cv plus R. But if it is high temperature, then what happens is that for vibrational, you will have to consider R, not R by 2. So for diatomic gases at high temperature, there is 1 degree of vibrational freedom, and for that you have to add R. So whatever you have got here, with that you have to add R, so it will become 7R by 2. And Cp is 7R by 2, so here it will become this plus R, so it will become 9R by 2. So these are the values of Cp and Cp for diatomic at moderate temperature, and these are the values for Cp and Cp for diatomic at high temperature. Next we come to polyatomic. Polyatomic means triatomic, tetraatomic, etc. Now for those molecules at moderate temperature, you will have 3 degrees of translational freedom, you will have 2 degrees of rotational freedom, and you will have at high temperature 3 degrees of vibrational freedom also. So at moderate temperature, Cv will be 3R because there are 3 degrees of translational freedom, so 3 times R by 2. 3 degrees of rotational freedom, so 3 times R by 2. So 3 times R by 2 plus 3 times R by 2 will be 3R. And Cp will be 4R. But at high temperature, there will be 3 degrees of vibrational freedom, and each will be R. So this plus 3R, so 6R, and of course Cv plus R is always Cp. So this is a very, very important chart. Just keep this chart in mind, that for monoatomic at moderate temperature, Cv is 3R by 2 and Cp is 5R by 2. At high temperature, Cv is 3R by 2, Cp is 5R by 2. For diatomic, at moderate temperature, Cv is 5R by 2, Cp is 7R by 2. At high temperature, Cv is 7R by 2, Cp is 9R by 2. For polyatomic, moderate temperature, Cv is 3R, Cp is 4R. And high temperature, Cv is 6R and Cp is 7R. Okay, then we come to the next formula, that is uh, specific heat for metals. So the formula is 3 into gas constant by molar mass. 3 into ideal gas constant by molar mass. So this is the formula for metals. 3 into gas constant by molar mass. So let's take an example. Suppose the example is iron. So 3 into 8.314 by 56. So if you take the example of iron, it will be 3 into 8.314 by 56. So, and the unit will be joule per gram Kelvin. If you want, you can take the value of R in calories also. So then 8.314 will be replaced with 1.987. See, 1.987 is very close to 2, so sometimes we take 2. So if it is calorie, 8.314 will be replaced by 1.987. So this is for iron. Okay, suppose if you have a mixture of gases, right? Suppose if you have a mixture of gases, then for the mixture of gases, Cp will be summation of, for every gas, the mole fraction of that gas into Cp of that gas. So for a mixture of gases, the overall Cp, it will be summation of mole fraction of that particular gas into Cp of that gas, and then the whole thing summation. So this is for a mixture of gases. Now you know that first law of thermodynamics, delta H is delta U plus delta Ng into RT. So if you differentiate both sides, d delta H by dt is equal to d delta U by dt plus delta Ng into R. So this is the first law if you have gaseous reactants and products, and after you differentiate both sides, this is what you will get. So if delta Ng is 1, then d delta H by dt will be d delta U by dt plus R. Meanwhile, you know that delta U is Cv into T2 minus T1. Now, all this is for ideal gas. Now, if it is a real gas, then P plus A by V square into V minus B is RT. So, these are all for ideal gases. For real gas, pressure plus A by V square into V minus B is equal to RT. Now, you know that in the difference between ideal and real gas is that when you are saying ideal gas, then the size of the molecule is neglected and attraction is neglected. So suppose in this equation, if the attraction is taken as 0, so if A is taken as 0, then the temperature will be P into V minus V by R. So if this is the temperature, then T2 minus T1 will be P into V2 minus V by R minus P into V1 minus V by R. So that is P by R into V2 minus V1. So delta U will be Cv into P by R into V2 minus V1. So delta H is delta U plus P delta V. So over here delta U you can replace it. So delta H will be Cv into P by R into V2 minus V1 plus P into V2 minus V1. So ultimately it is P into Cv by R plus 1 into V2 minus V1. So this will be the two formulas delta U and delta H for real gases in which attraction is negligible. So these will be the two formulas. Okay, next term we have calorimeter constant. It is the heat capacity of a calorimeter. So heat capacity of a calorimeter, formula will be delta H by delta T at constant pressure minus Cp of the contents. Normally contents means the copper, the water, everything. Sometimes we also use water equivalent. So calorimeter constant of any calorimeter means heat capacity of calorimeter. That means delta H by delta T at constant pressure minus Cp of the contents including water. So these are all the different theories related to specific heat, and now as always I will give you the 5 homework questions for the next class. Okay, question number 1. The mole fraction of nitrogen is 0.8, mole fraction of oxygen is 0.18, mole fraction of CO2 is 0.02. What is the Cp for the mixture? Options are 7R/2, 4R, 5R/2 and 3.51R. This is question number 1. Question number 2. Question number 2. What is the specific heat of iron at 25 degrees Celsius and 1 bar? And options are 0.4454 joule per Kelvin gram, 24.942 joule per Kelvin mole, 0.1071 calorie per Kelvin gram, and none of these. Okay, the next question is that boiling point of ethanol is 78.29 degrees Celsius. Boiling point specific heat of ethanol is 2.44 joule per gram Kelvin, and enthalpy of vaporization is 855 joule per gram. So question 3, ethanol liquid is being taken from 20 degrees Celsius to boiling point 1 kg. So the question is that what is the energy required? What is the energy required for this movement from ethanol liquid at 1 kg 20 degree to ethanol liquid at 1 kg boiling point? Options are 142.23 kilojoule, 997.23 kilojoule, 3.092 kilojoule and 21.68 kilojoule. And with the same data, there is another question, question number 4. ethanol liquid, ethanol gas. So C2H5OH 1 kg liquid to 1 kg gas at boiling point. What is the heat required? And options are 422.23 kilojoule and 997.23 kilojoule, 855 kilojoule, 1139.46 kilojoule. So ethanol liquid, ethanol gas, 1 kg boiling point, 1 kg boiling point. What is the heat energy required? Options are 422.23 kilojoule, 997.23 kilojoule, 855 kilojoule, and 1139.46 kilojoule. These are the options. So these are the 4 questions, and you have to do it by 9 p.m. tomorrow and submit it. So that will be all for this session, and I'll end this session now. Bye all of you.